Have you ever wondered how an electrical circuit reacts the moment you flip a switch, or when a sudden change in voltage occurs? It is not always instantaneous, and understanding this dynamic behavior is absolutely crucial for any electrical engineer. The time domain response of an RLC circuit describes how the voltage and current within the circuit components change over time after an input or disturbance. Essentially, it is the circuit's dynamic signature, revealing its transient and steady-state behaviors. This response is fundamentally determined by a second-order differential equation, which captures the interplay between the circuit's resistive, inductive, and capacitive elements. The core mechanism behind this behavior lies in how each component handles energy. Resistors dissipate energy, inductors store energy in a magnetic field and oppose changes in current, while capacitors store energy in an electric field and oppose changes in voltage. When these three elements are combined, their opposing and storing actions lead to characteristic oscillations and decays. The specific values of resistance, inductance, and capacitance directly influence a critical parameter called the damping ratio, often denoted by the Greek letter zeta. This damping ratio, along with the circuit's natural frequency, dictates whether the response will be underdamped, critically damped, or overdamped. Engineers typically determine this time domain response by first applying Kirchhoff's voltage and current laws to derive the circuit's governing differential equation. From there, powerful mathematical tools, such as the Laplace transform, are frequently used to convert this differential equation into an algebraic problem, making it much easier to solve. Once solved in the Laplace domain, an inverse Laplace transform returns the solution to the time domain, yielding an explicit function that describes the voltage or current as a function of time. This approach allows for precise prediction of how the circuit will behave from the instant of the disturbance onwards. A fascinating insight is that the roots of the circuit's characteristic equation directly correspond to the natural frequencies and damping behavior. For instance, complex conjugate roots indicate an underdamped, oscillatory response, often referred to as ringing. Real and distinct roots point to an overdamped response, which is slow and without oscillation. Real and repeated roots signify a critically damped response, representing the fastest possible return to equilibrium without any overshoot or oscillation, making it highly desirable in many control system applications. Ultimately, comprehending the time domain response empowers you to predict, analyze, and design RLC circuits with precision. It allows you to select component values that yield the desired transient behavior, whether that means quickly settling to a new steady state, intentionally creating oscillations for signal generation, or critically damping a system to prevent unwanted overshoot. This fundamental understanding is key to ensuring circuit stability and optimal performance in countless electronic systems.